So today we're going to talk about just generally continuous distributions. We might get through all of this and start talking about Bayes, but we'll see. We'll see where that ends up. So continuous distributions, we are distinguishing from discrete distributions. And I'm going to walk us through, again, continuous versus discrete, and we'll think about continuous distributions maybe in a different light, slightly different light. At the end of the day, do we really want them to be that different from each other? Do we want to think about them that differently from each other? I don't know. I don't really think of them as being very different. I just think of the values, the types of values that we get out of the distributions themselves. And there are three kinds of distributions, continuous distributions, that we'll touch on: uniform, exponential, and normal. We've already talked about uniform distributions, uniform discrete distributions, right? If you roll a die, like say a 6-sided die or a 36 or 32-sided die, there's an equal probability for any given outcome, right? So we look at that as being uniform, and we'll talk a little bit more about that. There is a uniform continuous distribution that doesn't look like dice rolls, but contains every possible value between, say, 0 and 1 or 0 and 10. And, the implication there being that there are decimal values. There's the exponential distribution, which we can think of as modeling the time between Poisson events. That's one way to think about exponential. And then there's the, everyone kind of knows it, normal distribution, which we use all over the place. We won't be digging that much into the normal distribution. We'll mostly do a couple worked problems. We'll write a couple functions and do some worked problems. And then, with the normal distribution, we'll code out an integration of the normal distribution just to see how we might do that, okay? It's not likely something we would ask you to do on an interview, at least not at this point, but it's good to understand integration, which I'm going to be talking about at multiple points in this lecture. Okay, so let's start at random variables. So, continuous. So we had discrete random variables before, right? We're going to talk a little bit about continuous random variables. And, kind of the idea here is that if you have, let's say, a random variable, continuous random variable from a uniform distribution, and let's say the bounds of that uniform distribution are between 0 and 1, of course we can have any value in between here. There's an infinite number of values, okay? There's an infinite number of values. So if we pull a random value out of here, it could be that, and maybe that's, 0.8134922 off into the distance, right? Maybe that's what that value is. Yes, I would love to screen share. Thank you. It's always helpful. There we go. All right. So, continuous random variables, and we're thinking about a uniform distribution, which, let's just, for the sake of this example, we'll just say a uniform distribution has every value that we can draw has equal probability, right? So the probability of drawing this 0.8134922 and so on is the same as the probability of drawing 0.9 0, 9, 1, 3, 2, etc. Those two draws have equal probability. Now, here's an issue, though. If we have a true continuous distribution, then this precision goes off to an infinite number of places, right? How do we answer the question? How can we answer the question? The probability that this random variable from the uniform distribution is equal to this, 0.813492, and so on. How can we answer that? This is actually an issue, because if we have infinitely precise values, like truly continuous values, and we're considering the space between 0 and 1, how many possible values are in between 0 and 1? Well, there's an infinite number of values if we're working with an infinite precision, which means that the probability of any given value is going to be 1 over infinity, which is about as close to 0 as you can get, right? So we don't necessarily ask the question, what is the probability of a specific value? We don't necessarily ask that. In a truly continuous way, we don't ask that. What we have to do is we have to put bounds on it, okay? We have to say, okay, well, maybe the question we're asking is going to be, what is the probability that x falls within certain bounds? Okay. So the way we were working with PMFs, right? And this sort of looks like a PMF kind of question, probability mass function. But for continuous distributions, we call these PDFs, okay? We call these PDFs, or probability distribution function. And you might see sometimes probability density function, both in our notes and out in the world for PDF. But the generally accepted form of this is probability distribution function. So default to that. So what is the difference between a PDF and a PMF? Well, a PDF doesn't give probabilities for distinct values, right? It can't, because we can't do that with a continuous distribution. We cannot get the probability, as I said, the probability that x is, specifically 0.1934 off into infinite number of places. What we can do is answer questions like, we can bound this in some way. We could say 0. Well, I don't remember what I was just typing, or just put in there, but 0.1342 is less than or equal to x, and this brings up a good question, which is less than or equal to 0.1343. We can answer a question like that, right? Because, at the end of the day, what this is the upper bound minus the lower bound, right? And maybe this is somewhere over here. It's the upper bound minus the lower bound over, if this is 0 to 1, over 1. Okay, so we could determine a probability if this is a uniform distribution. Otherwise, we might have to do a little more work, okay, if it's not uniform. So, weird. Go ahead and erase that. So we have this idea of a PDF, and it's bounded by an interval. But recall that a PMF refers to a specific value. It refers to a discrete value, right? That's the probability that, say, z is a bad one. Here, let's do the probability that y is, 7, right? Doesn't need bounds. 7 is this discrete value. And just to reiterate this, the probability of a single exact outcome in a continuous distribution is going to be 0, okay? The probability of a single exact outcome. The reason being, as I said, if we're dealing with infinite precision, then we have an infinite number of places. Then there's an infinite number of potential values between, say, 0 and 1. So anything divided by infinity is going to be about as close to 0 as you can get. All right. So let's sort of expand this idea of bounds, of a range, okay? Now, this is going to be a very high level, some very high level thought about calculus. Let's say we have a curve. And it looks something like this. So let's imagine that the area under this curve, the whole curve, is equal to 1. Imagine we draw a random value from this, and we're trying to determine the probability of that value. Now, as I said before, if we pick an exact point and we have infinite precision, then this exact point is, well, the probability of getting that exact point is 0. However, if we're dealing with a range, let's say this range, and here we've got, let's just think about this area. If we can determine the area of this, we can ask the question, what is the probability of getting a value between these bounds? And then we can just say, well, the probability of that is going to be this area divided by the entire area. This is going to be some fraction of the whole area. So again, this is that idea that keeps coming back around. The probability of A is going to be the cardinality of A over the cardinality of S. This isn't really different, except in this case, this area is A and the entire area is S. But we're thinking about this as being essentially the same concept. Now, how do we determine this area, right? How do we determine that? It depends, and that's the easy answer I can give. It depends. It depends on whether or not we can perform, just basic integration on the function. And if we know this function, and we know that it's possible to integrate it, well, we can just integrate it for these two bounds. Now, what do I mean by integrate it? I mean, we get the area under the curve, okay? We figure out the area of this exactly through integration as we would in calculus. Now, that doesn't mean necessarily that we have to do it that way. there's another way that we can approach this. Interesting. My drawing tablet just stopped working for some reason. But I can still see it on my main screen, so we'll go with this. Hopefully this won't be too messy. Okay. So I'm just going to make another plot here and do my best to make this work. So we have, something like this. And we're trying to determine the area between, let's say, this point and this point. One of the ways we can do this is we can subdivide these. We can split this into sections, okay? And we can follow this up to the curve and go over a little bit. Follow this one up to the curve. Go over a little bit. We can do this. And we can get areas for all of these. And we can just sum those areas. So notice here we just have a height and we have a width. So if this is H1, W1, we could get the height and widths for each of these sections and sum them together to get this area going up to here. And notice something, we do lose some information in here. Okay? So, we add some information or we lose some information. We lose some values. And that's okay. This approach, which we call a Riemann Sums approach, is going to give us an approximation. It's not going to give us the exact value. And you heard me say a word, Riemann Sums. This is just the sum of these rectangles. That's what we're seeing in this approach. Let's see if I can get my monitor to work again. 1 second. Oh, there. Hey. Started working again. I actually had to return my my drawing monitor at some point in the last couple months, hoping this one isn't failing too, but we'll see. All right, so we're going to start thinking about this, about continuous distributions with the uniform continuous distribution, okay? We're going to, like I said, cover 3 distributions: uniform continuous, exponential, and normal. And the uniform distribution is remarkably simple, right? It's something that we understand kind of intuitively when we call to random and get a float value. We get a uniform value between 0 and 1. It could be anything between 0 and 1. No value is more likely than any other value as far as we can tell. And the way that we think about this visually, I'll just do 0 to 1, is like this. It's a box, right? The theoretical distribution is going to be a box because, if this is the probability over here, and we choose, values in a random in some range here, there's equal likelihood for either of these values or this value or this value, all of them. are equally likely, okay? So the kinds of questions we might ask and answer here are, pretty straightforward and pretty easy to solve. So I might ask the question, what is the probability that x is less than 0.75? Well, if I look at 0.75, roughly there, maybe, it's all of this, right? Well, that's just 0.75 over 1. The probability that x is less than 0.75 is going to be 0.75. It's not really mysterious, right? We can see that pretty easily. If this was 19, between 0 and 19, then this probability would be 0.75. Well, we'd have to think about it, right? We'd have to multiply 0.75 by 19 and divide the result of that by 19. This is, just the subset over the containing set. That's all it is. And something to notice, I use this less than symbol. This is going to be equivalent to the less than or equals. We might as well just use less than. Less than or less than and equals are the same thing in a continuous distribution, okay? Due to that idea of infinite precision. Okay. So let's think about some other facets of the uniform distribution. What is our expectation? So this may not be immediately obvious, but we can just take the low bound and the high bound, okay? And just divide that by 2. That's our expected value. Pretty straightforward. If we were to throw values in there like between 2 and 19, that's just 21 divided by 2. And so our expectation would be 10.5. Where is that? That's, the exact middle value between 2 and 19. So I think that's pretty intuitive. Something that's not as intuitive is the variance, okay? The variance is going to be 1/12 multiplied by the high bound minus the low bound squared. I'm planning on making a video explaining this. It's not intuitive, but this does come up in other spaces, and I think it's interesting why this is 1/12 multiplied by the difference between the high bound and low bound squared. So that's all in good. Let's look at a way to create a pseudo-continuous uniform distribution, okay? This is something that may not make sense unless you review it. I'm going to try to talk through it in a simple way, and we'll just see. So I'm going to import choice, and I'm going to set up a random process for selecting ones and zeros. So this is just going to return the choice from 0 or 1. Okay? And now I'm going to make a list of binary. And let's do this, get binary, and let's make this, so we'll call this bit list, And I'm going to say for whatever in range, and we'll do 16 of these. Let's just get 16 bits. So bit list dot append get bit. Okay. And then we can return the bit list. All right, so this is just our random sampling process for a binomial distribution, right? We can see, let's print get binary, and we should see 16 bits. Okay, and we do. If I run this again, we see 16 different bits. If I run this over and over again, we're going to see these different bits. Now, if we ran this 1,000 times and we were looking at the sum of bits, then the expected value would be 8, right? We would expect to see 8 bits if we average these after a ton of samples. That's fine. That's not what we're going to do, though. Instead, we're going to apply a little bit of geometric decay. And if you remember, in a geometric distribution with a probability of 0.5, we could say 0.5 raised to the first power would be the first term, 0.5 raised to the second power would be the second term, 0.5 raised to the third power would be the third term, right? And these are, 0.5, 0.25, 0.125, and so on, right? We can keep doing this. And it's going to have the weight of the term, right? Every time we're cutting that in half. So we can take this idea and we can use it to put weight on the bits, okay? So the first bit, we can say, well, maybe that should be worth 0.5. And the second bit should be worth 0.25. And the third bit should be worth 0.125. And the fourth bit should be worth, 0.5 to the fourth power, and so on, right? And in this way, we're building a sort of tree, right? We can either get a 0 or a 1 on this first draw. We can either get a 0 or a 1 on the second draw, and so on. And we can kind of see how, in this case, any list of binary is going to be equally probable. And if we put weights on each of these, we're either going to add 0.5 or we're not going to, okay? Add 0.25 or we're not going to. Add 0.125 or we're not going to. And, if we had an infinite number of bits, we could, through summation of whether or not we add each of these powers of 0.5, we can construct any number between 0 and 1. So how do we represent this mathematically? Pretty straightforward, I think. It's just the sum from 1 to n, where n is the number of bits in the list. 0.5 raised to the I multiplied by the bit. And I'm saying bit sub I here. This is with the assumption, to be clear, this is with the assumption that, if this is a list of bits, the first bit is b sub 1, second bit is b sub 2, the third bit is b sub 3, and so on. This is a mathematical representation. Of course, in Python, this first bit would be b sub 0, and so on. So how do we write this in Python? Let's call this get float. And we're going to get a list of binary, right? What is this called? Get binary, I believe. Yep. So we've got this binary list, and we've got a float accumulator. We can just say for index and bit in enumerate the bin list, and we can start at the value 1. And then we can say float accumulator is going to be incremented by the bit multiplied by 0.5 raised to that index. And we can return the float accumulator, and we can return this binary list. Okay, so let's print one of these floats. And we'll see the float value in relationship with the binary that we used to create it. And there we have it. So 0.7453 and some change. This first value contributes 0.5. The second value does not contribute 0.25. The third value contributes 0.125, 0.0625, and every one of these ones contributes a little bit more. But notice we cannot get a value greater than 0.75 here. It's not possible. We can approach 0.75 if we have ones all the way off to the right forever, but we can never get to 0.75. Likewise, we can never get 1 in this scheme. We can get 0, but we can never get 1. It's just not possible in this. Okay. So that's a take on uniform. All right? That's one way for us to think about the uniform distribution through this lens of constructing that uniform distribution. The other is, simply what we were looking at visually. I think the uniform distribution is very intuitive, right? If we're trying to figure out the probability of getting a specific value between 2 and 19, we can do that. We can just figure out the bounds for that value and divide it by the whole. And, that doesn't look so difficult. It's kind of a basic arithmetic problem. Okay. So we're going to think about another distribution here, the exponential distribution. So what I want you to take away from this, if you take away nothing else, remember that the exponential distribution models the time between Poisson events. So what do I mean by that? Well, let's say we have a period of time. And maybe this is between 0 and 3 minutes. So remember, if we have Poisson events, they occur at some point within this. And we have a lambda, right? Let's say we have a lambda of 1, 2, 3, 4, 5, 6. If we have a lambda of 6, well, we can answer a question like, what is the probability that 7 things happen in 3 minutes? We can answer that question. That's not too hard. Now, here's the thing. These events were, if we just throw them at this timeline, they are going to want to be evenly spaced in some way. Let's imagine. They want to be evenly spaced. And then we can scatter them more and more so that they, look more chaotic as they do here. Or, more, there's a little more entropy here. They're not well ordered very well. So we can start thinking about these more in terms of the spaces in between these events, right? And we can start expecting an amount of time instead. And remember, time is continuous. Time is a continuous value, as far as we know. So we can start thinking of, well, if we have this lambda of 6 and in 3 minutes, what is the expected amount of time for us to be waiting? That's the kind of thing that we can start to answer. Okay. So there are some fairly nice formulas for these, for the moments, what we call moments of this distribution. You know, the mean and the variance, and the formulas for the PDF. Those aren't so bad either, right? With a PDF, we can answer a question: what is the probability of, say, waiting this amount of time between a certain number of events? Or with the CDF, we can answer a question like, what is the probability of waiting, 2 or less minutes, given this lambda. So lambda means the same thing here. That's essentially what I'm getting at. Okay, so I have a quick coding challenge for you here. This is just implementing some formulas. So let's put, I don't know, let's put 4 minutes on a clock for this. And you're going to code the exponential PDF, which is represented here. Your little your function names there. Exponential mean, which is very straightforward. Exponential CDF, okay, which we have a closed formula for, which is nice. You don't need to do a summation. And the exponential variance, which is here. And if you want to throw in an exponential standard deviation, do that as well. You should just remember what the relationship is between standard deviation and variance. Okay. So I'm putting, I'll actually put 5 on the clock. Go ahead and code these out. I am sorry for not having my mic on. I thought I clicked it on. Okay, so these are pretty straightforward. I'm going to go ahead and code these. I put the I put e and square root at the top of this. We don't actually need square root, but I'm going to use it for the standard deviation as it relates to the variance. Okay, so we'll start off with the exponential PDF. Pretty straightforward. So exponential PDF, and we'll pass in a lambda, right, which is our expected number of events, and we'll pass in x. And then we'll say if x is less than 0, let's return 0. And that's straight out of this, right? So if x has to be greater than or equal to 0, otherwise we return 0. Okay. And then we can just return lambda multiplied by e, and this is this equation here, raised to the negative lambda multiplied by x. Okay. So that should be that one. That should work. And we can code the exponential CDF, which is going to be very close to the exponential PDF. So I'm just going to change a few things here. We'll pass in lambda and x. Again, if x is less than 0, return 0. And here we can return 1 minus e to the negative lambda multiplied by x. So that's just a direct translation of this formula. Next, we've got the exponential mean, which we just pass in our lambda, and we're getting the expectation out of here. It's just 1 over lambda. And then finally, we've got our variance. Well, not finally. There's going to be one more. So let's do exponential variance. We'll pass in lambda, and we'll return 1 over lambda squared. Now, I'm just going to put in also the exponential standard deviation. All this is the square root of the variance. That's what standard deviation is for us. And that's why I imported that square root function. Okay. So my assumption is that all these work. We'll find out in a second. I've got a breakout that will utilize these. So I'll paste these in. And I'll save this. Okay. Oh, it looks like there's an error. Oh, let me fix that. Okay. 1 minus. So there is a little error in that code. If you've already copied it, you might want to copy it again now. I just fixed it. Okay. All right. So here we've got a pretty straightforward, a pretty common, what I'll say is a common exponential kind of problem that I will put up here. Suppose you're on a street corner trying to hail a taxi cab. Let x equal the amount of time in minutes that you have to wait. X follows an exponential distribution with a lambda of 0.1. So cabs arrive at a rate of 0.1 per minute. If we're thinking about 10 minutes, then that looks like 1 cab, right? What's the probability that you'll have to wait more than 10 minutes? What is the amount of time that you would expect to wait? And what is the variance of this random variable? So let's do 3 minutes on this. And do your best to answer these, and then we'll go over them. All right, so let's look at these one by one. All right, what's the probability that you'll have to wait more than 10 minutes? Okay, so more than 10 minutes, if we're thinking about this, we've got some timeline, and let's say 10 minutes is here. Now, we don't know offhand how to answer the question more than 10 minutes. What we can answer is less than 10 minutes, right? We can answer this question between 0 and 10 minutes. However, the assumption is that that we can invert this, right? We can take the complement of the result of the probability of less than 10 minutes. So we can just do 1 minus the CDF with a lambda of 10, right? Sorry, with a lambda of 0.1. And a time of 10. And remember, this 10 is not discrete, right? This is a continuous 10. This is 10.00000, and so on. Okay. So how do we answer that? 1 minus the exponential CDF. Lambda is going to be 0.1. And x is going to be 10. Okay. So let's see what that is. Looks like that's 0.367 and so on. And notice in this question, we didn't have to say, we're not saying x, less than 10 necessarily. What we're saying is, this can be inclusive of 10, right? Because it's not relevant whether it is or not. Does that make sense? It's a continuous distribution. 10 is the same from our point of view as 9.9999999 infinitely. Okay, so we get that answer. The next question, what is the amount of time you would wait to expect? Well, we've got the mean. That is our expectation. We can just grab this and set lambda to 0.1. So we would expect to wait, and I don't think this should be too surprising. We should expect to wait 10 minutes. 0.1 cabs per minute. It's, our expectation would be 10 minutes. The amount of time, what is the variance of this random variable? We can just call out to this exponential variance function, which I'll snag. We just plug in our lambda. And our variance is 99 minutes squared. Well, that's not the most interpretable value, so maybe we just want to instead use the standard deviation and see what that gets us. Okay, variance of about 10 minutes, or the square root of 100. So that's just some light application of the exponential distribution. The main thing that I want you to get out of this is that you can use the exponential distribution to model the time between Poisson events. Okay, so let's take 7 minutes, and when we come back, we'll look at the normal distribution. Okay, so we're going to start talking about the normal distribution. And, not sure what's happening there. Oh, there we go. I'm going to go ahead and quit out of that and start it back up. Okay, that looks a little better. All right, so the normal distribution is going to be familiar to most people, I think. It follows that classic bell-shaped curve, right? And we apply this in a lot of different areas. It comes up a lot. It applies to a lot of different measured phenomena. Everything from how we quantify IQ to the height of trees in a forest. These kinds of things tend to follow normal distributions. And we also apply these in spaces like the central limit theorem, confidence intervals, which are used in hypothesis testing and statistical inference in general, and in a lot of other places. So there is a sort of, how do I say this? A slightly intimidating looking formula for the PDF of the normal distribution. And this is it. So notice the constants and the tools that are used in this. So we've got a square root function, right? We have pi, and that is our pi. That's 3.1415, etc. We've got e, 2.71828, etc. So those are our constants, and then we've got these three parameters that we pass in to the PDF. The parameters of the distribution are mu, which is the mean, and sigma, which is the standard deviation, right? X is, you could say, the value for which we're looking for a something like a probability. Okay. So I'm going to have you code this up, and I'm going to give you a little snippet of code to be your target. That normal PDF of, if we're looking for 0.5 between 0 and 1, that should be somewhere around 0.3521. Okay. So you are going to code the normal PDF, given the mean and standard deviation. And let's give this 3 minutes. And whatever code that you get to at the end of 3 minutes, paste it in. If it's not complete, still go ahead and paste it in. Okay, if you have any code, go ahead and paste it in, and I will go ahead and start coding this out. So probably the first thing you're going to notice here is that this is a fairly messy looking function. And if I code this, I like to kind of keep track of it, do it in parts. So we're also going to need pi. So I'm going to say for math, import e, square root, and pi. Okay. So I'm going to get all of those. And we're going to call this normal PDF, where by default x is 0, mu is 0, and we have a standard deviation of 1. Okay. So that's a standard normal distribution, as it turns out, mu of 0 and sigma of 0. Sigma of 1, that is. Okay, so we'll do this in parts. Maybe I'll make this just slightly bigger. So we'll start with this chunk right here. This is going to be 1 divided by that sigma, and I'm just going to wrap as many things in parentheses as I feel like it. The sigma times the square root of 2 times pi. Okay, so that's our first chunk, and I'm just going to separate this out into a second chunk. This is going to be multiplied by e to the negative 1/2. Right? This is almost truly purely an organizational issue, this problem. And I'm gonna wrap this exponentiated operation because it's not e to the negative half, it's e to the negative half multiplied by the difference between x and the mean over sigma, and that result squared. So this is all kind of packed in, right? So negative 1/2 multiplied by x minus mu, and that is divided by sigma, okay? And so we've got this chunk right here that is also enclosed here. So, we have to exponentiate this by 2, and then we close the whole thing like so. And hopefully there are no mistakes in there. And I wouldn't be surprised if I have a mistake in there, is the thing. And that's why we want to test this against a specific value. So what I had said was 0.5, a mu of 0, and sigma of 1. And what we expect to see here is something like 0.3521. So let's print that, and hopefully we get the right result. .3521, roughly. Okay. So I'll paste that function in. And we'll start thinking about the question that we usually are trying to answer with the normal distribution. We're not usually trying to answer a PDF question. We are generally trying to answer a CDF question, right? So we've got some normal distribution, and what we're trying to answer is, what is the probability of getting a value, let's say, less than x, where x is, I don't know, maybe -3 or something like that, and our mean is 0, and our standard deviation is, I don't know, 2, or yeah, something like that. Now, there's an issue here in that we have a hard time getting this area using some kind of closed formula. We don't really have the ability to integrate this function very well. If you've done calculus, you probably realize this, you probably encountered this, that this function, the normal PDF function, is just incredibly hard to integrate. And so we're not going to do that. The classic way that people would find the area under the curve of something like this is they would look things up in tables or use computers to calculate these values. So we're going to do both. We're going to both look this up in a table, go through the process of reading a normal table, and then we're going to, I'm going to walk us through writing a function that will use an accumulator approach with Riemann sums to calculate the area under the curve for some value of x. Okay, so here's the thing. Classically, we might use a normal table. And I'm going to try to show you what this looks like. And I'm going to say offhand, I'm not a big advocate of this. So here is a normal table. And you might notice there are a couple things in here that if you haven't done this before, you might not really be aware of what these things are. So we've got this probability that z is less than or equal to z, right? So here's our little z over here. We're trying to calculate this area, the area there. When have we encountered a random variable z like this, unless when we were arbitrarily naming it? Turns out that we've got a process that we use to generate what's called a z-score. And that's what that little z is. That is called a z-score. So what the z-score represents, that is the count, or let's say, not the count, but let's say the number of standard deviations away from the mean. So that's interesting, right? That's interesting. So we're going to figure out how many standard deviations some value is away from the mean, and then we're going to look up on this table, and we're going to say, oh, well, maybe that value is 0.303 standard deviations, negative 0.303 standard deviations, and so we would look here at negative 0.3 or negative 3.0, and then we would go over here to 0.03, and we would say it's this. There's a 0.0012 probability if our z-score is negative 3.03 or negative 3.03 standard deviations away from the mean. We get this 0.0012 probability. So how do we do this? How do we calculate a z-score? And not why would we calculate a z-score necessarily, because this starts seeming a little bit cumbersome, right? This is like, wow, not only do I need to perform another calculation, but I need to also look things up in a table that is a little bit obtuse to start with. So I'll just close that. So how do we calculate the z-score? Essentially, if we have a normal distribution, then we are going to kind of constrain that normal distribution, okay? So that it fits a certain mu and sigma, a mu and standard deviation. So we normalize it. And what that means is that we set the mean to 0 and we set the standard deviation to 1. Okay? So if some random variable x, if x follows a normal distribution with some mean and some sigma, then we can define a new random variable. We can transform this to a new random variable z, where z is going to be x minus the mean over sigma. Okay? And as a result of this operation right here, we can see that this random variable z will follow a normal distribution with a mu of 0 and a standard deviation of 1. Then we can use this z-score to reference the table. So let's go through a specific example. And we'll do this end-to-end. We'll even look this up in a table, just to be old school, right? Because anymore, we've got statistical packages to do this. Oh, here, let me grab the actual whole question. So as I said, there are a lot of phenomena that follow, that tend to follow normal distributions, and we tend to be able to answer probabilistic questions. First, find the scores on the verbal on the SAT follow a normal distribution with a mean of 475. Okay, so we've got a mean, a mu of 475, and a standard deviation of 98. So first thing we're going to do is we're going to find the z-score. We are interested in the probability that somebody will score less than a 300, okay, on the SAT. Okay, so we are going to transform this. We are going to find the z-score of a score, a z-score of a less than 300, score on the SAT. Okay. So what does this look like? This is going to be, we can transform this. This is going to be the probability. Take this up here. This is again the probability x minus mu over sigma. We can transform this, right? We can transform this to the probability that we can perform this operation. Let me take the probability out of there. X minus mu over sigma is going to be 300 minus 475 over 98. Okay? And ultimately what we're asking here is the probability that z is less than or equal to the result of that. Okay? So our z-score here, which we often represent as phi, is going to be, or phi, I always say it wrong. Phi is going to be negative 1.79, okay? Or sorry, phi is our function. My apologies. So the result of this z-score is negative 1.79, and our function, to look this up in the table, we're finding this probability of negative 1.79. So how do we reference this table? So let me find this table first off. Interesting. It seems like that table has disappeared. I think I know where it is. Give me just one moment and I will track it down. We kind of really need the table to be able to answer this question. Okay, perfect. All right. So here's our table, and maybe I'll just make this a little bit bigger. And now I'll just get a screen capture of it actually. Okay. So if our z-score is negative 1.79, the way that we're going to read this is we're going to find negative 1.7, okay? It's down here, negative 1.7. Then we're going to follow this all the way across to the 0.09. Notice this is negative 1.7 plus minus 0.09. So we're going to go all the way over here and all the way down, and our probability is going to be 0.0367. So I'm not going to say that looking things up in a table is terrible. I think it's a lot nicer to use an actual CDF function from a package. So we could do that, but we have materials in Learn that show you how to do that. But instead, I'm going to code something out because, well, that's kind of our norm, right? Let's code something that solves this problem. And what we're going to do is implement something that employs Riemann sums. So let's say we have a normal distribution. What we're going to do is chop this up into rectangles. And we are going to get the area under the curve relative to those rectangles. So I'm going to call this normal CDF, and I'll do my best to explain this as I code it. So we have, let's assume x is going to be 0 by default. Mu can be 0 as well. So we'll just give this a, we'll assume the normalized normal distribution. And I'm going to set a width for these x values, okay? So for each one of these, I'm going to set a width, right? And for this, I'm just going to use 0.01. This is the kind of function that we'd probably want to play around with quite a bit to make it work better in various circumstances. But we're just, sorry, I said 0.01. I'm actually going to do 0.001. And as I'm coding this, you might think about some of the shortcomings of this specific function, not this approach, but this function. Like, what kinds of values might I not be able to handle very well would be the kind of question I would ask. I would ask myself looking at this. Okay, so x width. And now I am going to generate a series of values. Okay? So I am going to say, this is going to be a comprehension. Num for num in range. Okay? I'm going to go from negative 1,000 to 1,000. And I'm going to modify this as I go, right? This is just for num in range, negative 1,000 to 1,000, right? I'm covering all those numbers. And we're thinking about, how do I say this? We're thinking about this value num. So I'm going to build from here. I'm going to say x times 1,000. And x can have a decimal value, so I need to cast this to an int. And this is the range of x values that I'm considering. And what I'm going to do here is say num times x width. And now I've got a range of x values to work with relative to the input of x. So let's just print these x vals to take a look at this, what this might look like. So I'll just use the default values here. X is 0, mu is 0, sigma of 1. And let's find out what those look like. Okay? So this is what we're seeing. We're starting at negative 1, negative 0.9999, 0.99, 998, 997, 996, and so on. So this is relative. This is relative to x, but we want to be careful about the shortcomings of this, right? Because we're only going from negative 1 to 1, and we're hoping that this is going to work sufficiently well for problems that come across our path. And I think for the problems we'll look at today, they will work well. This will work well, but it might not work that well for other problems. And I want you to be aware of that. And I want you to think about how you might adapt this code to work with other problems. Okay? So I'm going to say for each value in xvals, the accumulator is going to be accumulating the result of this normal PDF, right? Where we pass in the value, mu, and sigma. And then that's going to be our height, okay? That's the height up to that point on the bell, right? On the curve. And then we multiply this by the width, okay? That's our rectangle right there. We're accumulating the volume of those rectangles, that is. And then I'm just going to put a little safety in here. If the value becomes greater than x, then we break, okay? Because we don't want to include all those x vals. We want to include only up to x. And then we can return the accumulator. So let's try to answer that same question that we just looked at, where let me just grab this. Find the z-score, for the probability that a randomly chosen SAT score will be less than 300. And let's go from there. All right, so x is going to be 300. And mu is going to be 475. That's our mean. And sigma is going to be 98. That's our standard deviation. So I can, I'll go ahead and plug these in, and let's see what we get. All right, so x, mu, and sigma. And let's find out. So it looks like that's 0.03707 or 0.0371 would be a nice round for that. And how does that compare to our other version of this? Well, before, what we got was the table value 0.367, okay? 0.0367. That's not too bad. That's within striking distance. Now, it's not perfect, but it is doing pretty well, okay? Things you might think about in regards to this problem. Increasing this range would be one thing, maybe increasing it to 10,000. That would be a way to possibly get better values. Increasing the range as well as decreasing the width, right? The smaller, the thinner those rectangles are, the more accurate you are going to get. But realize that in this x-vals, we're cutting off the leftmost value at 0. And, you know, if you're thinking about a normal distribution, this goes off to negative infinity on the left, goes off to positive infinity on the right, although those start contributing negligible values as you go. Okay, so let's look at a quick problem. And think about how to answer it. So a radar unit is used to measure speeds of cars on a motorway. The speeds are normally distributed with a mean of 90 kilometers per hour, so a mean of 90, and a standard deviation of 10 kilometers per hour, standard deviation of 10 kilometers per hour. What is the probability that a car picked at random is traveling at more than 100 kilometers per hour? So what I like to do with these in general is draw the problem. I don't need that middle there. So we've got a mean of 90, standard deviation of, you know, something around 10, right? And we want to know the probability that a car is traveling more than 100 kilometers per hour. Well, it turns out that that line of the standard deviation is the line, it is the value of x that we are interested in. And so what we're trying to figure out is the area of everything to the right of this. So the strategy here, if the sum of the entire area under the curve is 1, right? Then what we can do is get the area of this and say 1 minus that, okay? Again, the complement, it's going to come into play. So we've got a function that is going to help us with this. Let's define our x, right? X is going to be 100. And our mu is going to be 90. And our standard deviation, sigma, is going to be 10. Okay. So we're not really interested in this value offhand. Let's just take a look at what that is. Right, this is, when we look at that, this is the area left of 100, not to the right of 100. But let's just see what that is. So it looks like that's 0.841. We want the complement of that, 1 minus that, which is 0.159 roughly. So that's just the kind of example problem that you might encounter with the normal distribution. All right, so we have about so we've covered the materials to cover for the for continuous distributions. So what we can do, got some time here. We can start in on and get a sense of conditional probability. Okay. Fair warning, even though this is scheduled for tomorrow, I might have to call off. I just had my second COVID vaccine, and starting to feel it. So I might hand off to Clark and do a bunch of function practice. And honestly, like, that's likely a better path either way. I think this group has needs a lot more practice in Python, and so we might skip conditional probability and spend the next few lectures focusing on function practice, both with me and Clark, depending on the class. So we've talked a lot about probability, right? We've talked a lot about this kind of question where we have, the probability of some event. Okay, so probability of event 1. Let's call this event 1. What we haven't really talked about is the probability of event 1 given event 2. And for simplicity, we'll often do this, the probability of A given the probability of B. So this is a different kind of question. And how we interpret this is that, given event B has occurred or will occur, right? Given event B has occurred, what is the probability of A? Okay. So essentially what we do here is we limit the sample space in order to start answering this question. And we've seen a little bit in the way of intersections and unions and whatnot. Let's say we have a diagram, call this S, and we have A, and we have B, okay? So I won't switch colors back, but let's say that's A and B. And let's give this some arbitrary values, right? Let's say that this part of A is 1, the intersection is 2, and these are sort of like area values. And this part of B is 3. So the question we want to answer here is, what is the probability of A given B? Well, if we're only considering the part of A that is in relation to B, and B is this presupposed event that has occurred or will occur, but has a direct effect on A, then we can think about this as being the probability of the intersection of A with B over the probability of B. Well, what is the intersection of A with B? That's obviously 2. And what is the probability of B? That's 2 plus 3, or 5. So that's a simplification, let's say, of how we think about this, but it's a nice way to visualize it. We've limited the sample space from which we draw A, right? We've limited that to this part right here. So in this case, it's 2 out of the area of B, which is 5 from this representation. So there's a little law here, right here. This is called Kolmogorov's definition of conditional probability. Kolmogorov definition of conditional probability. And that's simply this. A given B is equal to the probability of A intersect B over the probability of B. We can start extrapolating from this, and we can build a more intuitive, maybe more complex vision of conditional probability out of this. So here's the thing. If we have, again, I'll go to a Venn diagram because I think these are helpful here. We have, in this case, we just have A. Let's just say we've got A, like so. And then we have, this is all part of S. And then we have these sections within within S that are B1, B2, and B3. Let's say we don't know the area of A. Well, how can we start constructing this? Well, the way that we can start building this idea is we've got the intersections of these, right? If we're trying to construct A, we can construct it from its parts. We can construct it from this part, and this part. And these are just the intersections of A with B2. This is the intersection of A with B3. This is the intersection of A with B1. If we can do that, then we can just add those together. And what we get with this is A is going to be B1 intersect A unioned with B2 intersect A unioned with B3 intersect A. Okay? So we can think of this in a slightly different way, and the way we might start thinking about this, well, let's look at Kolmogorov's definition. Kolmogorov's definition is A given B is equal to the probability of the intersect of A with B over the probability of B. Well, what if we multiply both sides of this by the probability of B? Right? Well, we can rethink this definition. The probability of A intersect B is going to be equal to the probability of A given B multiplied by the probability of B. Okay, so this is important. We can take this back up here and apply it to A. Okay, so we can rewrite this area of A in a form that will allow us to conceptualize how to calculate the probability of A. So we can rewrite this as the probability of A would be, well, let's pull this out, and this is going to be the probability of A given B1 multiplied by the probability of B1 plus the probability of, and this is this one, probability of A given B2 multiplied by the probability of B2 plus the probability of A given B3 multiplied by the probability of B3. This ends up being very powerful. This is called the law of total probability. So let's leave it at that, and I will review those. If we cover conditional probability extensively, I'll review all this. But this seeds the idea, I hope. If I'm feeling well tomorrow, I'll teach tomorrow, and we might do conditional probability, although we might focus on coding and just do a bunch of practice coding problems. I think that's where people need the most practice still. So let's call it there.